So moving from hydrocarbons to compounds that contain oxygen, which are of course amongst the more fun ones to play with. So spectrum D is that of pentanethriol. Explain the base peak at 59. Well, pentanethriol is this one. Now, if you remember, a nice rule of thumb for how oxygen-containing compounds are going to break up is some of the best fragments come when you break the bond that's attached to the oxygen carbon. So in other words, we break this bond or that bond. Now, if we break this bond here, well, then we're left with this nice little cation, this super-duper special cation there. Break that bond there, and we get the same thing because this is a nice symmetrical molecule. So whichever one of these nice bonds to break, we're going to end up with CH3, CH2, CHOH+, which shockingly has a mass of 59. So therefore, this 59 is the peak that one would expect from breaking the bonds associated with the carbon-oxygen. So pentanoic acid, we're asked about peak 73. There's pentanoic acid and its molar mass is 102. Well, how do you get down to 73 from 102? You lose C2H5, which weighs 29. And here is the obvious C2H5 right there. So lose that, we're left behind with this peak here, which has a mass of 73. Notice, by the way, the nice big peak at 60. We'll be coming back to that later on. Spectrum E again, pentanoic acid. What are the two acylium ion fragments one would expect for the molecule? Well, the acylium ion fragments are the ions that you would have left when you break the bonds to the oxygen carbon. So let's start that one first, break that. And that would give us this, 1, 2, 3, 4, 5, all the carbons there, because we just lost that OH there, and triple bond to the O, that's what makes it the acylium ion, and this has, when you add it up, a mass of 85, as you'd expect, because you've lost OH, which weighs 17, 102 minus 17, 85. Now let's break this bond here. Break that, then we got this fragment left over, very common fragment for a carboxylic acid, a mass of 45 because you've got two oxygens at 32, a hydrogen 33 plus a carbon takes it up to 45. Where are those? Well, there's the 45 and there's the 85. Present, not huge, but definitely present. Now, spectrum F is of an isomer, 2,2-dimethyl-dimethylpropanoic acid. Identify the peak at 57. Explain why it is so dominant. So there's the peak at 57. There's the molecule that we're looking at. And remember, 57, that stands for a C4H9. Does anything out here leap out at you as being a C4H9? And the answer is right there. Okay, well, how would we get that? Well, we'd break that bond there. That is, of course, one of the bonds we really want to break. That is the bond to the oxygen's carbon. Okay, and when we break that, we're left behind with our C4H9 fragment, which, as we have seen before, tertiary carbocation, super duper and stable. Finally, spectrum E, going back to pentanoic acid, there is that peak at 60 that I mentioned. Where does it come from? And the answer is it comes from the nice McClavity rearrangement. So we get down to where we have the electron that goes is from one of the lone pairs on the oxygen. So we have the radical cation of the oxygen. We then have, if you count the carbons, carbon 1 there, carbon 2 there, carbon 3 there, carbon 4 there, and then the fifth carbon, the methyl group at the end, just poking off, don't really care about that. What is important is one of the hydrogens on this carbon that makes that pseudo six-membered ring. So therefore that pops onto that and we have the cleavage that we expect. Looking at the peaks, there is a mass of 60. So remember the McClavity arrangement. This sixth part of the six-membered ring hydrogen goes on to the oxygen. We then break associated with that, the bonds there, leaving us with this little fragment that's boring, but this fragment here that has the mass of 60. Now, why would spectrum F not have this peak? Well, we need a six-membered ring. So oxygen is 1, carbon 2, carbon 3, carbon 4. It doesn't matter which one of these I use for carbon 4, the hydrogen would only be the fifth member of the 6-membered ring. So you simply don't have enough carbons there.